Good evening, ma'am. Am I audible?
Good morning, sir.
Good evening.
Sorry, sir. Good evening, sir.
Good evening. Good evening. Are you doing the regular revision?
Good evening, sir. You are audible, sir.
Okay, ma'am. Thank you. Thank you.
Yes, sir.
Very good.
Sir,
Yes, ma'am.
sir, you can start, sir.
Okay, ma'am. Okay. Good evening, students. In this class, we are going to continue our discussion on electromagnetic induction. In electromagnetic discussion, we are going to start with motional EMF. So let me share the whiteboard with you. So the concept which we are going to discuss today initially is motional EMF. Okay. So for that, initially you need to consider a cylinder. So let me draw a cylinder here. cylinder means it is nothing but a rod, okay, and you all know very well that the cross section of a rod looks like a cylinder. So that's why I am considering this as a cylinder, okay. The cross section of this rod looks like a cylinder, okay. So this is the rod, and this rod is actually moving on this direction. So let me show you the direction. The rod is moving along this direction, okay, with velocity v. This is the velocity of this rod, and it is moving along the right hand side, and this rod is actually moving with this constant velocity v perpendicular to a uniform magnetic field, okay. So it is not actually moving in vacuum, it is actually moving in a uniform magnetic field. So that uniform magnetic field is represented by this cross mark, okay, and the magnetic field is directed perpendicular to the screen and inwards, okay. So the magnetic field is directed perpendicular to the screen and it is directed inwards, and this end is represented as P, and this end is represented as A, okay. So the magnetic field is represented as capital letter B. This is the magnetic field, and the length of the conductor. The length of the conductor is represented by small letter L, okay. So here this conductor or the rod moves with a constant velocity v in a direction perpendicular to the magnetic field represented by the blue color cross marks. So the magnetic field is perpendicular to the velocity and it is directed into the screen, okay, into your laptop or phone screen, okay. You should imagine in that way, that is in 3 dimension, it is directed into the screen. So now this rod is actually moving. So how can you calculate the EMF? Because this rod, when it is moving with velocity v in this magnetic field, an EMF is actually induced in this rod. So that EMF is actually called motional EMF, okay. That EMF is called the motional EMF. So in general, the motional EMF can be calculated using the integral form. So the motional EMF can be calculated using the integral form. E equal to integral B cross B dot dl, okay. Dl means the movement of the conductor in the magnetic field, the small length, that is called dl. So in general, the motional EMF is represented by E equal to integral B cross B dot dl, okay. So here we are going to consider the 2 cases. In case 1, when the 3 vectors, okay, when the 3 vectors V, B and L, vector V, vector B and L, they are perpendicular to each other. When all the three vectors are perpendicular to each other, then your motional EMF, okay, motional EMF is the maximum value. So this is otherwise called dynamic EMF. So E suffix D, it will have the maximum value that is equal to BVL. Okay, case 1, when the three vectors V, B and L are perpendicular to each other. So when the three vectors are perpendicular to each other, the motional EMF or the dynamic EMF has the maximum value that is equal to BVL. Now we are going to consider the next scenario, case 2. As far as case 2 is concerned, if any two of the vectors, okay, if any two of the three vectors are parallel or anti-parallel to each other. Parallel means the angle is 0 degree between them. Anti-parallel means the angle is 180 degree. Okay. So parallel or anti-parallel to each other, then the dynamic EMF is actually 0. Okay. The dynamic EMF is minimum and it is actually equal to 0. Okay. So these are the concepts of motional EMF or dynamic EMF, and I think you will be able to understand the concept here. That is the equation for finding the motional EMF. I think you all can understand this thing. Okay. Do you have any doubt in this? The concept of motional EMF. Do you have any doubt?
No, sir.
Okay. Now we will be discussing a special case of this concept. Okay, a special case of this concept of motional EMF we will be discussing now. And what is that case? That is motion of a straight conductor. Okay, motion of a straight conductor on a railing in uniform magnetic field. So this is the next concept which we are going to discuss. So for that, we are going to draw a circuit now. This is the railing. So in this railing, you are having a resistance here. Okay, you are having a resistance here, represented by capital letter R. And you have a rod, that is the straight conductor. Okay, the straight conductor can be represented by this thing. You have a straight conductor here. Straight conductor is having the length small letter L. The length is represented by small letter. and this railing is actually moving with velocity v. This straight conductor actually, not railing, is moving with velocity v. That is a constant velocity. So here you are having a magnetic field also. And that magnetic field is represented by this cross mark, capital letter B. This is the magnetic field. And this rod actually can move towards the right hand side, or it can move towards the left hand side. Okay. And for that, the distance between this resistance. So distance between this resistance and this rod, it is actually x. Okay. The distance between this resistance and R is x. Now, what is the EMF induced in this rod? Okay, what is the EMF induced in this rod? So, first of all, the EMF induced in this rod is represented by E equal to BLB. Okay, BLB, because the magnetic field is perpendicular to the screen and directed inwards, and you have the velocity towards the right side direction and L. So E equal to BLV is the induced EMF. And what is the current flowing through the circuit? Okay, current flowing through the circuit is represented by I equal to E divided by R. So E divided by R means that is BVL divided by R. So here, due to the movement of this rod, you will be getting some induced EMF on the rod, and due to that, you will be getting induced current on the rod as well. Okay. So I think you can understand this. The rod is moving, and due to that, you will be getting induced EMF on the rod, and due to that, you will be getting induced current also. That induced current causes some retarding force. Okay, it causes some retarding force on the metal rod, because according to the Lenz's law, you know very well, the direction of induced current flows in such a way to oppose the change that causes it. Since the change is the movement of the rod, so the induced current flows in such a way that to oppose the movement of the rod. So the retarding force, okay, retarding force exerted on the metal rod is retarding force on metal rod, that is represented as F suffix m. So that will be given by B squared L squared B divided by R. Okay, B squared L squared B divided by R. So here you are having an external force acting on the rod that is responsible for the movement of this rod. Okay, so that external force and this retarding force should be equal. Then only the velocity will be constant. Okay, the rod is not accelerated. Instead, it is moving with constant velocity v. So when it has to move with the constant velocity v, then the retarding force on the metal rod, it is actually equal to the mechanical force required for the movement of the rod. Okay, the force which is used for moving the rod mechanically. So that mechanical force and this retarding force should be equal. Then only there won't be any acceleration of the rod. The velocity will remain constant. Okay. So here F external. Okay. F external or the mechanical force is equal to the retarding force, that is B squared L squared B divided by R. Now the rate of doing work, mechanical work. So the rate of doing mechanical work can be represented as power. So P external is equal to PM, okay, because the external force is equal to the retarding force on the metal rod. So due to that forces, you will be having some power, okay, that is power is nothing but the rate of doing mechanical work. So that is represented by PM equal to F external dot vector V, okay. So you all know very well the equation for finding the power. Power is nothing but force into velocity. So the same formula here we are using. So this F external into velocity means B squared L squared V squared by R. So that power is represented by B squared L squared V squared by R. That's the power. Okay. So due to the power, actually you will be having some heat dissipation across this resistance. Okay, heat dissipation. So that heat dissipation can be represented as I squared R. Okay. So that heat, I think I can write here. So the heat dissipation across the rod. Okay. So heat dissipation across the resistance. Heat dissipation across the resistance. It is P. Okay. Thermal power. Thermal power means heat dissipation across the resistance. That is P equal to I squared R. So that will be I, we already know BVL by R. So here that is BVL by R, the whole square into R. So that will give you B squared L squared V squared. So here I squared means that will be R squared, okay. B squared V squared L squared by R squared multiplied by R. Finally, you will be getting B squared V squared L squared by R. This is the heat dissipation. Okay, so these are the concepts related to the motion of straight conductor on a railing in uniform magnetic field, and you may be getting numerical problems on this as well. So far we have discussed the concept of this motional EMF when the movement of this conductor is perpendicular to the direction of the magnetic field. Okay, but we have not considered any situation when the movement of the conductor is inclined at particular angle theta with respect to the magnetic field. Okay, in that case, what you should do? You have a magnetic field, and when the velocity of the movement of the conductor is inclined at particular angle theta instead of 90 degree, then what is your formula? Okay, what is your EMF formula that we are going to discuss now? So when the conductor moving, okay, when the conductor is moving at particular angle, with its length in a uniform magnetic field. That angle can be considered as theta. Okay, so in that case, what is your EMF equation? So that thing we shall see E equal to B into V sin theta. Okay, B into V sin theta into L. Instead of V, you have to use V sin theta. Okay. So this is the concept. Okay. Then we are going to discuss the next concept. The next concept is EMF induced in a rod rotating in a uniform transverse magnetic field. Okay. We have a rod. So this is the next scenario. EMF induced in a rod rotating in a uniform magnetic field. EMF induced in a rod rotating in a uniform transverse magnetic field. So when it is rotation, you need to consider a circle now. So let me draw the circle here. This is the circle. This is the center, and from the center you will be having a rod. Initially, the rod is in this position and it may move like this from here to here. So this point is P prime. This point is P. The angle between this point and this point is delta theta. Okay. We can mark this with another color. So this is delta theta. So the length of this rod is L. The length of this rod is L. Okay. And here the rod is rotating with angular velocity omega. And here you have the transverse magnetic field represented by the cross marks like this. So the rod is rotating in the transverse magnetic field. Okay. Inside this circle also the magnetic field exists. The rod is moving now in this transverse uniform magnetic field. The rotation of the rod is having the angular velocity omega. Then what is the EMF? Okay, what is the EMF induced between the ends of this rod? So that EMF is nothing but EMF equal to half B omega L square. Okay, EMF equal to half B omega L square, where omega is nothing but 2 pi into F. Omega is the angular frequency and F is the frequency. Okay, right. So this is the formula for the EMF when you have a rod rotating in a uniform transverse magnetic field like this. Okay, and you can also have the other scenarios also. You can have a conducting cycle wheel. Okay, so let me do it in the next page. You have a rod like this. And this rod can rotate about its geometrical axis in a uniform magnetic field. Okay, in a uniform magnetic field. So that magnetic field can be represented like this. It is directed into the plane of the paper. So it is rotating about its geometrical axis. Okay, it is rotating about its geometrical axis means this axis actually. The axis passing through the center. Okay. About this axis, the rod is rotating with velocity omega, with angular velocity omega. It can rotate. Okay. And this length is actually L by 2. Quite obviously, this length. Okay. And this length is L by 2 and L by 2. This is L by 2, this is also L by 2, where L is the length of the rod. Okay. So here, this is the edge of this rod. So here you have the point Q, and here you have the point P. Okay. And here you may have a point B. Here you may have a point A. Okay. So the distance now from here to here, it will be L by 4, quite obviously. From here to here, and from here to here. That is L by 2. This is L by 2. This is also L by 2. This rod is now rotating with uniform velocity in a uniform in a magnetic field. So here, what is the situation here? Okay. So you can consider the situation like this here. Here you see from Q to this point P, you may be having like a situation that is this is like a battery. Okay, this is like a battery. So here to here, at the point B, you may be having a battery. Okay, why it is called a battery? Because a potential difference is generated at this point B. Okay, at this point B, a potential difference is generated, and that is also due to the rotation of the conductor. Okay, this is the negative terminal. And this is the positive terminal. Why I am drawing a battery here? Because we may be getting a potential difference developed at these points B and A. Why potential difference is that is due to the induced EMF. Okay. So here you will be having positive terminal. Here you are having negative terminal. The points can be represented like this. So this is Q. This is Q. And here you have EMF EQO. The center point is O. Okay. So this point is EPO. So this point is P. So due to the rotation of this rod in the magnetic field, an EMF is generated at this point B and at this point A. That is represented as EQO and EPO. Okay. And the EMF values, now we can write the EMF values. That is EPO is equal to EQO. That will be equal to 1/8 B omega L square. So both are same. Okay. EPO equal to EQO equal to 1/8 B omega L square. But here these two EMFs are equal in magnitude, but as you can see here, they are opposite in direction. Okay. So here positive terminal is there. So the battery, the current is flowing from here towards this point O. Here also you have a positive terminal. So current is flowing from this point to O. Okay. So both EMFs are equal in magnitude but opposite in direction. Then what is the EMF now? EMF between points B and A. What is the EMF between points B and A? Similarly, points P and Q. What is the EMF? That is EPQ equal to EPO minus EQO. So both EMFs are same, so you will be getting 0. So similarly, between points A and B, your EMF will be 0. Okay. Between points A and B, your EMF will be 0. So this is how you can find out, okay, the EMF of a rod rotating about its geometrical axis. Okay, about its geometrical axis. But the previous scenario which we have discussed, the rotation of the rod is as a whole. Okay, the rod as a whole rotates like this. This is a different scenario. Here the rod is rotating about its geometrical axis. This is a different scenario. I think you can understand this. So this is what the motional EMF is all about. And now we are moving on to our next concept. That is rotation of a coil in a uniform magnetic field. We shall move on to the next concept, that is rotation of a coil in a uniform magnetic field. Rotation of a coil in a uniform magnetic field. So for that, let us consider the magnetic field represented by these lines. This is B. So all these lines represent the magnetic field. And you have a coil like this. The coil is little bit tilted. Okay, it is not at this angle, it is little bit tilted. So it is not exactly with this angle, it should be inclined at an angle theta, so that the plane of the coil can be represented like this. The plane of the coil. That is area. So here you are having the axis of rotation. Okay. Here you are having the axis of rotation. Let me represent that by this. Here you can see the axis of rotation is like this. So this is rotated like this. So magnetic induction is here. The plane of the coil is A, inclined at an angle theta. So what is the magnetic flux now? So magnetic flux phi, you know very well the formula B dot A. So that will be BA cos theta. And now the coil is rotating. So there is a change of flux. Okay, coil is rotating with angular velocity omega. So theta is replaced by cos omega into t. Okay, cos omega into t. Because of the displacement. Okay, the angular displacement theta can be represented by angular velocity into time. So theta equal to angular velocity into time. So that means instead of theta, you should put cos omega t. So if you have n number of turns, then the magnetic flux is given by n BA cos omega into t. So due to the rotation of the coil, there is a change in magnetic flux linked with the coil. Okay. So what is the change in magnetic flux? d phi by dt. d phi by dt. You need to differentiate this. So that will be n b a omega sin omega minus NBA omega sin omega t. So we all know very well the EMF is given by minus d phi by dt. So E equal to minus d phi by dt. So from this equation it is NBA. It is NBA omega sin omega into t. This is the EMF generated due to the rotation of the coil in the uniform magnetic field. So here this NBA omega is nothing but the maximum EMF that can be linked. Okay, maximum EMF that can be linked with the coil, and the notation of that EMF can be taken as E naught. E naught equal to NBA omega. Okay, NBA omega, and of course this small letter E can also be replaced by capital letter E. So E equal to E naught sin omega t. From this equation, you can understand that the EMF generated due to the rotation of the coil in the magnetic field varies sinusoidally. Okay, at different positions of the coil, you may be getting different values of EMF. So that maximum value of EMF is modulated by this factor sin omega t. Okay, sin omega t. Now, what is the total current? Okay, what is the total current flowing through the coil? That is I equal to E by R. Okay, I equal to V by R, like that. The Ohm's law. So I equal to E by R means E naught by R sin omega t. Okay, sin omega t. So this E naught by R can be replaced by I naught. So we can write like this: I equal to I naught into sin omega into t, where your I naught is equal to E naught by R. Okay. So this is how the EMF produced during the rotation of the coil in the magnetic field varies. Okay. And due to that, you will be having current flowing through the coil as well. That also varies like this: I equal to I naught sin omega t. Okay, right. So for different positions of the coil, you will be having different values of EMF, and you will be having different value of current as well. So all these things you need to understand very well in order to solve the problems. Okay. Then we are moving on to the next concept, that is self-induction. So what is meant by self-induction? Can anyone tell me? Yes, students, self-induction, can anyone tell me? Does anyone know about that, self-induction? Students, anyone knows anything about that? You can unmute yourself and you can talk. Self-induction. Anyone knows about that? Okay. Self-induction means you are having a coil and the current passing through the coil. Okay, you are actually allowing current through the coil, and current through the coil should change with respect to time. So when the current flowing through the coil changes, you all know very well that current carrying conductor can generate a magnetic field around it. So when the current flowing through the coil changes with respect to time, then the magnetic flux linked with the coil also changes. Okay. So due to this change of magnetic field, you will be getting an EMF induced, and current is also induced in the coil. So this induced current actually opposes the change in magnetic flux. This phenomenon is called self-induction. Okay, this phenomenon is called self-induction. So let me draw a circuit and then explain it to you. So here you are having a circuit like this. So here you are having an inductor coil, just any coil. Okay, normally any coil you can have here. So this is the coil, and here you are having a cell, okay, of EMF E. You can represent it by some other color so that you can understand it better. Here you are having a cell of EMF E, okay. You are having a cell of EMF E, and this is the coil, and here you are having a key. Key is nothing but a switch, and here you are having a rheostat. And what is a rheostat? That is used to change the value of current. That is called a rheostat. So here you can see you will be having a rheostat. Circuit is like this, and due to the EMF you will be getting a current flowing through this direction. So here the current is flowing through this coil, and that current can be varied using this rheostat. Okay, and due to the changing current, there is a changing magnetic field around the coil. Okay, the changing magnetic field induces an EMF. So that EMF is called the back EMF. Okay, that EMF is called the back EMF. So this back EMF actually opposes the growth of magnetic flux. So the magnetic flux is now directly proportional to current flowing through the coil. So phi is proportional to current flowing through the coil. When you remove the proportionality, you have to put a constant. That constant is L. L is called the self-inductance of the coil. Self-inductance means the ability to generate a back EMF. Okay. So this is self-inductance of the coil. L is the self-inductance of the coil, and the SI unit of L is nothing but Henry. So SI unit of L is Henry, represented by the letter capital H. So L is nothing but a constant. Okay, L is a constant for a coil, and the EMF. Now we can write the equation for EMF. EMF E equal to minus d phi by dt. So minus d by dt of, instead of phi you can write Li. So that L can be taken outside, di by dt. So EMF E equal to minus L into di by dt. So this is how you can relate the EMF with the self-inductance. And this di by dt can also be written like this. When it is the current is changing from I1 to I2, okay, in time t, then your EMF can be represented as average EMF. Average EMF equal to minus L into I2 minus I1 divided by t. So that will be L into I1 minus I2 divided by t. Okay, this is the average value of the EMF flowing through the coil. Okay, so here what is the meaning of this inductance? Okay, L. What is the meaning of this inductance? L. So L is nothing but the ability of the coil. Okay, L is nothing but the ability of the coil to oppose the flow of current. To oppose the flow of current. Okay. So here you can see L is nothing but the ability to oppose the flow of current, and here you can see that inductance. Okay, inductance can be 0 for a thin wire. Okay, L can also be 0 for a thin wire, because for a thin wire your resistance can't be 0, but the inductance value can be 0 as well. So this is what self-inductance is all about. Okay, and of course we have some more concepts related to self-inductance. So the first thing we can see is self-inductance of planar circular coil. Okay, self-inductance of plain circular coil of small area. Self-inductance of plain circular coil of small area. So when you have a circular coil like this, having the radius capital R, what is the self-inductance value of this? So that I am going to write here. L is equal to mu naught n square pi capital R divided by 2. So that means your L is proportional to n squared, and it is also proportional to R. So if the circular coil is placed in any medium, then it is also proportional to the relative permeability mu R. Okay. Here I have just put mu naught. When the circular coil is placed in air medium or vacuum, I can use this. But when it is placed in any medium of relative permeability, then you will be having the proportionality relation. L is proportional to mu r. Okay. These are the equations. Okay, these are the equations for the plane circular coil. And we shall keep it this much for this session. And I will be giving you 5 questions today for your test. And that 5 questions will be forwarded by madam to you. And you need to complete the solution for the 5 questions. Okay, after 8 o'clock. Okay, after your next class is over. I think the next class may be biology or chemistry to you. After that class is over, you need to solve the 5 numerical problems and you need to send the answers immediately to madam. Okay. Thank you so much for joining the session. And we shall meet again in our next class.
Thanks, sir.
Thank you.